Yeah, I try to not to go too long.
Okay,
Hopefully
okay,
I'll finish.
Yeah. How are you recently?
I'm fine. It's all teaching. I have to.
Okay.
That takes a lot of time.
Yeah.
Otherwise, I hope I can visit Boston more.
Yeah, definitely. Yeah.
Yeah.
So besides the symmetric mass generation, machine learning, what else are you interested in recently?
Also, like some quantum information, like
Okay, I see.
entanglement dynamics, shadow tomography, things like.
Yeah. Interested to know more about that.
Yeah, I think there's a lot of interest nowadays in measurements, how to prepare many-body states, non-trivial many-body states. So I think there's a combination of correlated condensed matter or correlated material and maybe quantum information measurement, things like that. Yeah.
Right. Yeah.
Hi, Simon. Yeah, nice to meet you here over Zoom. Yeah. I may give the same talk few weeks later, but hopefully you won't be bored.
Sorry, I was muted. Sorry, that's fine. I was saying I might have to leave early anyway, so it'll work out well. When are you talking in Syracuse?
What? Talking?
When? Do you know
I forgot. I thought it's a few weeks later. I need to check my schedule then. Yeah, I forgot.
That's good.
Yeah, definitely. I'm very happy to talk there as well. Yeah.
Don't worry, it's always good to hear it more than once anyway.
Okay.
Yeah, so Jovan, do you think we can start now or wait for a few more minutes? Yizhuang, do you think?
Yeah, I'm fine.
Okay, yeah. So maybe I can start recording. Let me see how to do that. Okay. So hi everyone. We are very happy to have Yizhuang You from UCSD today to talk about symmetric mass generation. Yizhuang, please take your room.
Yeah. Thank you very much. Thanks, Jiewan and Zhuven, when inviting me. And actually, I did a lot of works with Zhuven recently, and we wrote a review paper on symmetric mass generation. So this is the we put that on symmetry, and then it's also Simon invited us to do that. Write that review, so thanks for that. And then the archive version we will update pretty soon. So the previous archive version contains some mistakes. So I recommend you read this paper on the journal website. It's I think open access, so everyone can download. Okay, so today's talk is essentially about this symmetric mass generation. I will only focus on one story which we review in this review paper, which is about symmetric mass generation in 1+1D. But that's actually already tells us a lot of things about symmetric mass generation on different aspects. So I think that's my plan. Okay, so symmetric mass generation, what's that? So we all know fermions can have mass. And then symmetric mass generation is just a novel way to give fermions a mass. So before talking about this novel mass, maybe let's first review what we learn about or what we know about fermion mass. The most conventional way to give mass to fermions is called fermion bilinear mass. So the setup is you consider that there are some relativistic fermion in d-dimensional space-time, such that the action of the fermion field can be written as this bilinear form, where you may have some Dirac fermion, which you can put a mass term here. And mass term is just a bilinear form of the fermion. And this psi bar is just psi dagger followed by the gamma zero matrix for Dirac fermions. But you may also think this also apply to Majorana fermions if these fermion fields are real, and then it's just a convention. You just redefine psi bar. But anyway, in general, fermion bilinear mass, no matter it's a Dirac mass or Majorana mass, generally takes some form like this. And by taking this form, then we can start from this kind of action and take the action principle. We take the derivative of action with respect to the field. So that gives us a equation of motion, or the saddle point equation. But this equation of motion essentially tells us that the fermion will propagate with a dispersion relation like that, or you can say it's an on-share relation, which means the fermion energy and the fermion momentum will satisfy a relation that is standard dispersion relation of massive relativistic fermion. And then there will be an energy gap between the upper band and the lower band. So this is the single particle spectrum of the fermion. So in terms of the many-body physics, then in the ground state, the many-body state of the fermion will occupy all the lower bands. So if you want to create any fermion excitation in the system, you will have to overcome this gap. So the system is gapped in this sense. And then when you overcome the gap and create a single particle excitation, the excitation will follow a dispersion like that, which means if you push it with push this fermion with some force, it will not immediately, it will generate some acceleration, which has a F equals ma kind of acceleration. Then this m mass is also associated with the curvature of the dispersion near the bottom of this dispersion. So in either sense, you can call this a mass. Either you can say the mass corresponds to this gap, or you can say the mass corresponds to this curvature here. And there's another way to think about mass. It's in fermion correlation. So we can calculate, because this is a field theory, you can calculate two-point function of the fermion by inserting the fermion operator into this path integral, and then it can be shown that this fermion correlation will exponential decay is as long as there's a mass here, and the decay length will be inversely proportional to the mass parameter here. So it seems that there are many different ways to define fermion mass, and that's what we know about fermion bilinear mass. But what is the suitable definition of fermion mass beyond this free fermion limit? Because beyond this free fermion limit, we can no longer solve the equation of motion in the presence of the fermion interaction. Fermion interaction meaning that in the action, you may have some full fermion term, then you can't really write down a simple equation like that. And then this dispersion relation doesn't make sense. So everything that I talk about that has to do with this dispersion relation doesn't really make sense. But you can still define the notion of, because that is because in the presence of interaction, you may not even be able to define quasi-particle. However, we can still define correlation function. This is still a way to define what do we mean by fermion mass. So one can still calculate correlation and say that if the correlation decay, for example, in a power law manner, with the power being the 2 times the scaling dimension of the fermion, then that corresponds to a gapless fermion phase. However, if the fermion has a gap, usually in the correlation function, you will have an exponential decay correlation function, and the inverse correlation length can be used to define a mass. And then this is also consistent with the fermionic excitation gap in the many-body spectrum. So when we come to this many-body physics, we can use correlation length or excitation gap to define fermion mass. So then the symmetric mass generation. So when we talk about fermion mass generation, essentially is how can we have a system of fermion, how can we create a situation where the fermion correlation is short range and the many-body excitation has a gap. So that's essentially what we mean by mass generation. So it does not necessarily mean that we need to write down a mass term as a fermion bilinear term in our action. So that opens up new possibility to create this so-called excitation gap or short-range correlation in the fermionic theory. So this diagram concludes the most general, at least up to now, what we know, general schemes of giving fermion system a mass, in the sense that gapping out the fermion system. So the whole diagram relies on the assignment of symmetry. So symmetry plays a very important role in classifying different kinds of fermion masses. So if you have a symmetry group, and then let's say the fermion field transform under the symmetry with some representation, which I denoted R psi G. So this representation depends on the fermion field, and it's a representation of the group G. So given this information, you can try to classify all different approach to generate fermion mass. So first of all, you can ask whether there exists symmetric bilinear mass. So meaning that if I write down side by side this operator, is this operator symmetric under G already? If that is true, then I can safely open up a bilinear mass without breaking symmetry, and I'm very happy with that. So that's one possibility. You just explicitly turn on this term. However, if there does not exist any symmetric bilinear, meaning that any bilinear form of like mass term like this will somehow break the symmetry, then you have to make a choice. Then you can ask, at this point, do I need to preserve the symmetry? Do I want to preserve the symmetry? If I want to preserve the symmetry of the action, then it's more difficult. But if I don't want, if I don't care this symmetry, even this action has a symmetry, I don't want to preserve it, then probably I can spontaneously break the symmetry, meaning that the actions still have the symmetry, but my ground state can break the symmetry, such that in my ground state, I can spontaneously generate some of these fermion bilinear mass. And in that way, you can still give mass to fermion at low energy. And that's actually Anderson-Higgs mechanism of spontaneous symmetry breaking mechanism. So that's also rather conventional, which we know already. But what we want to discuss more recently actually is this new direction where you can preserve symmetry and give fermion a mass by so-called symmetry extension. You actually need to extend the symmetry group into a larger group and try to do something there. And then I won't enter that detail, but within that class of ideas, there's another criterion, which is about whether the symmetry group is anomaly free. If the symmetry group is anomaly free, then you can just open up the gap and without generating other topological order. But if it's not anomaly free, meaning that you cannot trivially gap out the fermion, then probably you either the system still remains in a conformal field theory state, which does not have a mass, or the system, if you really want to give an excitation gap to the many-body system, then there's one possibility is to use anomalous topological quantum field theory. So in that case, we say it's a topological mass. But today, we are going to focus on this symmetric mass generation, which means that fermion bilinear, all the fermion bilinear term breaks the symmetry, but we still wish to preserve symmetry at the ground state. So we should think about something more innovative, and then we should try to see how to create a mass there. And this symmetric mass generation applies to the scenario where the system does not have any G anomaly of the symmetry. Okay. So essentially, if you are not allowed to turn on any fermion bilinear mass because that breaks symmetry, then probably the only thing you can add to the action is to add fermion interactions. So usually symmetric mass generation is realized by interacting fermions, by applying interaction to these gapless fermion systems. But then what is the designing principle? It's not like any interaction you can just put into the system that will do the job. Usually it's not the case. So there are two actually criteria. One is called the kinetics. The other is dynamical criterion. The kinetic criterion is basically say that the system should not have any anomaly, because anomaly is an obstruction towards gapping. So that's, you need to have anomaly cancellation. And the dynamic criterion is that the interaction really need to leads to this gapped phase, meaning that there exists interaction to drive the system into a new RG fixed point where all the low energy fermions are trivially gapped. So the condition that there exists such an interaction is a dynamical criterion, because you don't know a priori. You have to do, usually you have to do some simulation in order to determine whether the interaction will work. But so that is actually the gapping condition. However, in 1+1D, it turns out that these two conditions are equivalent, and there is a deep relation between each other, which is revealed in Druven's recent work. So let me talk about this 1+1D example first. So this 1 plus 1D example of symmetric mass generation, the name of the model is called 3450. It has a very weird name, but this 3450 basically correspond to our charge assignment to certain chiral fermion in 1 plus 1D. So the model contains 4 chiral fermions in a 1 plus 1 dimensional space-time. So you have 1-dimensional space, 1-dimensional time, and the fermion has this standard gapless fermion kind of action. And there are 4 of them labeled by this index A, goes from 1 to 4. And there will be, I will add some interaction later, but for now, let's not worry about this interaction. So this 4 chiral fermion field in this theory, I want to specify what kind of symmetry it has. So if you just look at the theory has a very large symmetry, it has a U4 symmetry. Basically, all the 4 fermion can rotate. But let's not think about that large symmetry. Let's focus on a specific U1 cross U1 prime symmetry. Because later on, you will see interaction will break the full U4 symmetry, but still preserve this U1 cross U1 prime symmetry. So what do I mean by that? That means under U1 and U1 prime rotation, the fermion field will gain a phase factor. But different fermion field indexed by this A equals 1, 2, 3, 4, they gain different phase factors. And the phase factor that they gain has to do with the charge carried by the fermion. So the charge assignment is such that psi 1, 2, 3, 4 fermions separately carry charge 3, 4, 5, 0 under the first U1 and carry charge 0, 5, 4, 3 under the second U1 prime. And that's the charge assignment. And also, this fermion, you notice that there's a velocity term here, which specifies whether the fermion is left or right moving. So the assignment, the model is such that the first 2 fermions is left moving with a positive velocity, and the second 2 fermions is right moving with a negative velocity. So maybe the most clear way to summarize what I said just now is this picture that I have 4 fermions. They are all chiral fermions in 1D, 2 left moving, 2 right moving. And in the bracket, it is the charge assignment under the first U1 and the second U1. And that's it. That's the model. So this model, you can also view this model as a one-sided boundary of a multi-layer 2 plus 1 dimensional integer quantum Hall insulator. And every layer contributes a Hall conductance, assuming, so the Hall conductance is given by VQ square, assuming E square over H is 1. So in terms of the unit Hall conductance units, then, so for example, the psi 1 layer will contribute, I think, 9 units of Hall conductance for the first U1 and 0 unit of Hall conductance for the second U1 and things like that. So so there are, because we have 2 U1 symmetries, so we can define 2 Hall conductance, sigma and sigma prime, like that. And then the anomaly-free condition essentially is saying that you shouldn't, anomaly-free meaning that this 1 plus 1 dimensional system should be viewed as a standalone 1D system. So it shouldn't rely on the 2-dimensional bulk, which means that the 2-dimensional bulk should have a trivial Hall conductance. Trivial meaning that the Hall conductance must vanish in both U1 and U1 prime symmetry. So if you just add up the Hall conductance contribution from each chiral fermion, then you can show that the assignment of 3450 is very nice in the sense that it nicely cancel out all these Hall conductance. It's because 3 square and 4 square minus 5 square is 0. So that's a famous Pythagorean number, a triple of a Pythagorean number. So that's why the assignment is like 3450. And more generally, that's not sufficient yet, because there might be a mixed anomaly between U1 and U1 prime. So we also need to check that. So maybe the most general way to check the anomaly cancellation is to take the charge vector, which is this Q correspond to the charge assignment of the fermions. So there are 2 charge vectors correspond to 2 different U1 symmetries. So you require that this Q, K, Q equals 0, where K is the K matrix, which describe the chirality of these fermions, essentially. Okay, so however, we just checked that the system, when you assign the charge in this way, then it's anomaly free. However, this U1 cross U1 prime symmetry is still very restrictive, in the sense that it forbids any backscattering on the free fermion level, meaning that there is no trivial mass term. Because if you write down a trivial mass, no matter whether by trivial mass, I mean trivial bilinear mass. So if you want to write down any bilinear mass, no matter it's the Dirac mass, which look like this, or Majorana mass, which look like this, it necessarily need to take one fermion from one chain, let's say, from one chiral fermion to another chiral fermion, right? Or you want to generate a pair of fermion between these lines. But no matter which way you do, you can check. There's no way that this operator carries no symmetry charge, because all these chiral fermions, no matter under the first U1 or under the second U1, they have distinct charge assignments, 3, 4, 5, 0. None of them is the same. So no matter you take one fermion from here to here, then you violate charge conservation. If you try to simultaneously create two fermions like this and this, you still violate charge conservation. So any these mass terms will violate charge conservation, and it's forbidden by the both of the U1 symmetry. Of course, this both U1 may be an overkill, but at least it shows that there's no possibility to turn on any bilinear mass between any pair of these chiral fermions. So what but we have just argued, or we have just checked that it's the system is anomaly free, meaning that there is in principle no obstruction towards gapping. So you should be able to gap out all these left and right moving fermions simultaneously. And I also want to say that the system is also free from gravitational anomaly that I didn't mention previously. So it seems that there's no obstruction towards gapping, but there's no way to do that on the free fermion level. So that must be an interaction-driven gapping term. So the correct SMG interaction, the interaction to drive the system from this gapless chiral fermion to the gapped fermion phase is actually proposed by Yizhuang and Xiaogang back in 2013. And this interaction was recently verified by numerics in our more recent DMRG numerical work. So the interaction term, if you write down on the field theory level, it is a 6 fermion interaction term, 1, 2, 3, 4, 5, 6. It contains 6 fermions. So it seems to be a very complicated interaction. And you can also write down this interaction term on the lattice. For example, you can realize this chiral fermion as the boundary of a 2-dimensional lattice model of an integer quantum Hall, and then you can try to apply this interaction on one of the edges and see what is the result. So that is actually the calculation we do in this work, where we perform a DMRG simulation of these interacting fermion systems on one side, where we start from a 2D integer quantum Hall state and then apply interaction only on one side of the edge. And then we just focus on that side of the edge where we apply interaction, and we measure fermion 2-point function. And then what we see is that this fermion 2-point function, as a function of the separation of the fermion operator, which is along the x direction, it decays in a power law manner if the interaction strength is very small. However, if we keep cranking up this interaction G1 and G2, which we collectively denoted as G, when G exceeds certain critical value GC, what we see is that this fermion 2-point function start to decay exponentially as a function of the distance. You may forget about this noise. This is because the DMRG simulation has some truncation error. So that's the real data is here. So you can see
a little bit more about where this 6 fermion term comes from. I mean,
yeah. I'm going to explain that very soon. So let me first show you the effect. So at least these numerics give us some confidence that this is a correct interaction. And actually, the history comes the other way around, because Yizhuang and Xiaogang, they derive these 6 fermion from gapping conditions. So I'm going to talk about that very soon. But let me first mention the significance of this result is that it demonstrates a new possibility to regularize chiral fermion on the lattice. At least this is in this 1+1D model. And hopefully, of course, we wish that these ideas can be generalized to 3+1D model, which is more interest of more interest to us. So the idea is very early known as mirror or domain wall fermion approach, which dates back to Ichton and Preskill, that if you have some chiral fermion, you try to regularize that, and you can try to introduce the mirror sector and try to apply interaction in the mirror sector and to trivialize the mirror sector or to completely gap out the mirror sector such that it decouples from the gapless chiral sector. Then you can realize the chiral fermion. So with both mirror and chiral sector, the full model can be written on a lattice, no problem. So now if you apply the interaction, then you really achieve a lattice regularization of these chiral fermions. So that's the goal. But then the question is actually as you ask, why SMG interaction is so complicated? Why involve 6 fermion? Why is that? And in fact, we can even show that Wang and Wen's 6 fermion interaction is already the most relevant interaction allowed by the so-called gapping condition. Meaning that if you try to design anything simpler, it's anything, I mean, any interaction that is simpler than that is not going to work. So for example, you may think, can I do that on the 4 fermion level? That's not going to work. So any 4 fermion interaction is not going to give you a gap. So that requires us to understand this gapping condition, which is the dynamical condition. What kind of interaction will gap out the fermion? That's also very important. And in order to analyze that, in Juven's paper, what they do is that they perform a bosonization, bosonize the fermion field into e to the I phi, where phi is some scalar, some compact boson field. So, okay, so because I have 4 fermion, I still have correspondingly 4 boson, and the boson field will be described by a Latinger liquid theory whose Lagrangian is given in this form, which contains some K matrix describe this Berry phase term and some V matrix describing the Latinger parameter in general. And the K matrix essentially is describe the chiral fermion. So you have 2 left moving mode and 2 right moving mode. It sets the velocity of the fermion field. But when we try to add interaction to this system, so the first line describes the gapless limit, the free fermion limit of this one-dimensional system. And then if you add interaction, it turns out this 6 fermion interaction can be interpreted as some cosine term that add to this compact boson theory, cosine L dot phi. So phi is the vector which contains phi 1, 2, 3, 4, and this L is also a 4-component vector, which tells us how to combine all these phi fields together in the cosine term in order to generate a gapping term. So this L, there are 2 different interactions that has been added to the system, G1 and G2, and which is correspond to the interaction vector, these 2 vectors. It turns out. So now comes the gapping condition. The gapping condition is this condition. So that means you cannot arbitrarily write down some 4 fermion or 8 fermion or arbitrary fermion interaction. Any interaction will correspond, any backscattering interaction will correspond to some kind of this vector. But this vector is not arbitrarily designed. These vectors must be designed in such a way that it satisfies this condition. So let me explain why there is such a condition. So this fully gapped boundary can only be consistently achieved. So by condensing a maximally set of bulk excitation. So when I talk about bulk excitation, let me remind that our idea is to view this chiral fermion as the 1 + 1 dimensional boundary of a 2 + 1 dimensional U1 cross U1 gauge theory. Where originally I say it's a U1 cross U1 quantum Hall insulator, but you can try to gauge it, and the bulk becomes a gauge theory. And then this gauge theory automatically basically enforce symmetry on the boundary by gauging the symmetry in the bulk. So now as a gauge theory, you can talk about bulk excitations in the gauge theory. So the bulk excitation correspond to all these vertex operators, all these gauge charge, basically. This operator creates gauge charge in the bulk. And then the idea to gap out the boundary turns out to be you just need to condense all these bulk gauge charge to the boundary. But there's a condition for this gauge charge to condense on the boundary. That is, this gauge charge must be self-boson and mutual boson. Because in the gauge theory, it is possible that gauge charge can have mutual braiding. It's just like anyons. And then maybe sometimes due to some non-trivial effect, Chern-Simons effect, this gauge charge can carry non-trivial statistics. So you don't want those things to happen. Because when that happens, you can't really treat this gauge charge as independent boson and condense them. And then, but if you can condense the gauge charge, then you can argue that this boundary will enter the Higgs phase. And in the Higgs phase, everything is gapped. So there's no gapless degree of freedom remaining at low energy. So the idea is to achieve a fully gap phase by condensing this gauge charge. But the condition to do that is this gauge charge is self-boson and mutual boson, meaning that there should not be any mutual or self-statistics. And the way to calculate the statistics is using this formula in the Chern-Simons theory, turns out, in the bulk. And then in the bulk, that condition basically leads to the gapping condition on the boundary. So when this condition is satisfied, then all these operators are condensable. And then, so we call them condensable operator. And then you also want to check that this actually is also neutral. The operator that you condense actually is also neutral under U1 plus U1 transformation, such that the interaction doesn't explicitly breaks the symmetry explicitly.
How much of this structure is related to, the details of the model here? The fact you have this 3450 model, for example, and it's abelian and lives in 2 dimensions.
Yeah. I'll talk about that.
Is all of this determined by that? Or?
So you can see the 3450 coming from this charge vector Q. So when we assign a fermion with different charge, then you have this Q vector. So this L vector also needs to be, you don't want to, you want to have an inner product which is 0, meaning that when you perform a symmetry transformation, this cosine term, when you perform a symmetry translation, meaning that phi goes to Q times theta, and then phi plus Q times theta. So you want the symmetry.
Sure. But it needs to be abelian. This would not immediately generalize to non-abelian.
Yeah. This doesn't immediately generalize, but maybe it generalized to the Cartan subgroup of the non-abelian case. So that still provides some constraint, but that's not a full constraint. So the full story about non-abelian cases, I think at least not fully clear to me yet, but this is one condition. So you basically need to have this charge vector being mutual boson and also satisfy the symmetry condition. Julian, you have a question?
You can make some comment. One thing is that this model, although present in a way, say, view the 1 plus 1D chiral fermion theory as a boundary of 2 plus 1D bulk, I think the whole statement doesn't really require having this 1 plus 1D theory living on the boundary of 2 plus 1D bulk at all, because it's anomaly free, so it can exist. The reason we want to put on 2 plus 1D bulk just for convenience to have a fermion doubling with both chiral fermion and mirror fermion sector, and we gap a mirror fermion to left over with the chiral fermion theory at the end. However, if the purpose is just try to gap the chiral fermion by its own, then we don't need to put it on the boundary of 2 plus 1D bulk. And another thing following this is the 2 plus 1D bulk is finite width. So you can just view this quantum degree freedom as some several extra degree of freedom truncate the extra width to the same dimension in 1 plus 1D. So the whole system can still be viewed as 1 plus 1D, even if we have a finite width 2 plus 1D. And I think that part should be clear to the audience, hopefully. And another comment is, I feel the U1 times U1 prime, the symmetry layer doesn't really require to be gauged for the argument on this slide. I think we can just keep the U1 as global symmetry.
I try to make an analogy to anyons, so where the.
But we cannot. Yeah, that's totally understandable. But that's true. Yeah. That's true. Yeah, relay anyons certainly is thinking about dynamical gauge field. That's probably easy. Even for
doesn't need to be gauged on boundary.
Even for big on gauge non-dynamical field, the conditions still hold.
Yes.
Right.
I mean, I should think of them as just a Toft anomaly cancellation condition, right?
It's actually related. I'm going to talk about that. Okay, maybe I can say that. So
let me say one more thing to Simon is that this model is nothing special at all. It's just an anomaly-free model. You can take any charge you want. 3450 is not special. It's just simplest chiral fermion in 1 plus 1D with U1 charge. But it's not special at all. Take any U1 and possibly even non-abelian and Cartan subgroup. I think similar construction will work. And this design is a principle design based on the relation between anomaly-free condition and the statistics of choosing a set of operators as an ending of some extent objects to the 2+1D or higher dimension, one higher dimensional bulk, and check the statistics conditions. And that condition, I think I mentioned to you when we met at the Syracuse University. I kind of tell you this principle, but I cover it's too abstract. And this notion is also related to what people are checking about this so-called generalized central charge beyond the central charge of gravitational anomaly, CL minus CR, the coefficient. There's a higher central charge. But that notion is exactly relates to this gapping condition by checking the statistics of operators extend to the higher dimensional bulk. The design principle should work in higher dimension, just that checking statistics of extend operators in higher dimension is more complicated, possibly required to do some surgery on higher dimensional manifold with some link invariant wanting to check those things. And how to relate these operators that can end on the boundary, how do you choose the correspondence between the interaction term as a deformation and the statistics of this extend operator in higher dimension. How to relate them is something more tricky. But anyway, yeah, that's a comment. Thanks.
Yeah, so at least in 1D, 1+1D, there is some systematic understanding. So the question we are facing here is that we are given the charge assignment of this fermion, which is specified by the charge vector Q, and we try to design interactions that can add to this fermion system to gap out the fermions, where the interaction is specified by these L vectors, which appears in these cosine terms, which specify these cosine terms. So the relation, it turns out that the solution to this problem is you take your charge assignment multiplied by the K matrix that give you your L vector. So you can design interaction based on your understanding of the charge assignment, given the fermions K matrix, which specify the chirality of the fermion. The reason that this is a valid solution, because these solutions simultaneously unify the three conditions. One is anomaly cancellation condition. That is the first condition, that this condition equals 0 says Topological anomaly free. And then the second condition is symmetry requirement. You require that under U1 transformation, your interaction shouldn't violate the symmetry. So the L vector and the charge vector should have trivial inner product. And then also the gapping condition, meaning that you require the cosine term to be consistent with each other in the sense that this condensable operator can simultaneously condense on the boundary, and that should have trivial braiding, self-braiding, and mutual braiding, that this braiding statistics condition, it must also vanish. But you can see these three equations essentially is the same equation once you notice that L is related to Q by K times Q. And when you substitute that equation into here, then all these three equations is essentially the same thing. So this is basically the designing principle, that if we start from the charge assignment, which is the Q vector 3450 and 0543, and then we can multiply that with the K matrix that give me the L vector, which is this two column vector again. So basically, that means I just need to apply interaction to the system where I take the first fermion to the third power, second fermion to the fourth power, third fermion with a Hermitian conjugate to the fifth power, and then something like that. That should be a valid interaction. But you can see this interaction is too complicated. It contains, let's say, 3 + 4 + 5, 12 fermion interaction. So is there any simpler ones? So I should say that these L vector essentially, it only specify two independent condensable operator, but actually all the condensable operator in the system, by condensable, I mean all the operator that satisfy these trivial mutual statistic and self-statistic condition, they actually forms an operator algebra. And the operator algebra, in that operator algebra, all these condensable operators are arranged on a lattice. And it is a set of operators which all takes the similar form as a vertex operator, where this L vector is taken from the space that is spanned by this L1 and L2, which are the solutions that we obtained just now, and then also intersect with all the Z4 lattice. So Z4 lattice is all the possible operator in the system, and this space spanned by L1, L2 is the is essentially the submanifold in this system where the operators are condensable. So all the condensable operators are arranged in this lattice, where the origin of the lattice correspond to the trivial operator or identity operator. And then these are also operator we obtain. But you can see this lattice is actually contains other smaller operator, meaning that the length of the operator is shorter. Length of this vector is shorter. What's the significance of the length? Well, the operator scaling dimension, it turns out that in this system is associated with this length. Is 1/2 L transpose L. So L is this length of this, L is this vector. So at least this is the scaling dimension of this operator at the free fermion fixed point. So of course, we want to start from the free fermion and apply the interaction, drive it to a gap phase. We wish that the interaction is as relevant as possible. That's you don't need to pay a huge effort to drive that. So you usually want to choose the shortest vector. So you search on the lattice and choose the shortest vector. It turns out to be these two vector. And then these two vector, you just now reinterpret as 6 fermion interaction. So this vector, you just read out the first fermion, you need 1. The second fermion, you need to put the dagger and put it twice. But you cannot have psi 2 at the same point, right? So there must be some point splitting implemented by this partial X operator. And then the third fermion, there's also 1. And the fourth fermion, you have 2. And then that's one interaction. That's the other interaction. That's the idea to design the 2 interactions. So the interaction.
Sorry, can I ask a question?
Yeah.
About the gapping condition. You have this L transpose K inverse L. As 0, could it be like 0 mod 2 pi, or does it have to be 0 exactly?
What happened here?
Yeah, I think we lost the connection.
I can comment and maybe Yizhuang can comment later.
Oh, sorry, I just lost, sorry. Maybe Julian, you can continue comment.
I think it's a nice question, it's a great question. Naively, if you just want to have a trivial statistics, it could just be 2 pi integer for that 2 pi times some integer, so that condition doesn't seem to require the vanish of the LK inverse L to be 0. But I think for safety, usually we do require that. I think this is a subtle question. Probably we will not discuss that. No, but it's a good question.
Yeah. In the bulk for anion statistics, it turns out the trivial is you can mod 2 pi or mod integer in this case, but for gapping a CFT, it turns out the condition is even stricter. Yeah.
So these operators look like, what I would normally consider them irrelevant operators, right? Even in 2 dimensions, right? Because they have so large numbers of fermions, and yet they only seem to work at weak coupling, where I ought to be able to trust perturbation theory.
So you can't trust the perturbation theory at the free fermion fixed point. That's the point. Yeah. So
say again.
You can't trust the perturbation theory at the free fermion level, because this SMG is a non-perturbative interaction effect, meaning that this interaction need to be strong enough in order to drive the transition.
Sure. So that would make sense to me if, therefore, you found the right phase at very strong coupling, because then your theory is not reliable.
So the point is that you need to view this theory as you need to start from the SMG transition fixed point. That transition point has a CFT. You need to take that CFT as your starting point, and then you can reliably analyze the theory. You can't take the free fermion fixed point as your starting point. That's not going to tell you anything. That free fermion fixed point is just telling you free fermion is stable under all the perturbative interaction. So I think that's actually
I thought at one point you had a picture which showed that you got the right spectrum, or the right power law behavior, even for very small.
I'm going to show that soon. Yeah. I'm going to explain this. Yeah.
Okay.
So at weak interaction, the interaction has a very large scaling dimension, but you can show that the scaling dimension can actually be tuned until it becomes relevant. It can be tuned to a point where it becomes the space-time dimension. Then the interaction start to become relevant. Then you enter the SMG phase after this point.
Oh, I see. So the SMG phase is at relatively large G then. I misread your old plot. Yeah. Okay.
Yes. So you shouldn't analyze the scaling dimension of the 6 fermion interaction term at the free fermion fixed point, which is here. When the interaction strength is 0, then the scaling dimension, you would see the answer is 5, too large, much larger than space-time dimension. But there's a non-perturbative effect. It is because even if you turn on the interaction and it flows to 0, perturbative, for example, here, I turn on interaction by this much, it flows to 0, and the scaling dimension. But at this point,
sure, that makes sense. Sorry, I thought your old plot was saying that was true even for very small G, that you were in an
yeah, not the small G.
Okay.
G,
so then I agree. Yeah.
We need to have a finite GC, and the GC is a finite value of 5, something like that. Yeah.
Okay.
So it is a that's what I mean by it is a non-perturbative effect. It's not a interaction perturbatively cannot lead to any non-trivial effect, but you need to add that non-perturbatively. And the way to reliably analyze this non-perturbative effect is to go away from the free fermion fixed point and go to this fixed point. Go to the fixed point where the interaction is marginal, and then you can analyze this physics there. So essentially it's like that. And the reason that this interaction, although it looks perturbative, but it still have an effect, is because even if you turn on the interaction originally, for example, to here, it flows to 0. But during the flow, when the interaction flows to 0 during this process, it renormalizes, the interaction renormalizes the Lartinger parameter. And as the interaction renormalizes the Lartinger parameter controls the scaling dimension of all operators in your CFT. And then the Lartinger parameter can be renormalized in such a way that it reduces the interaction, the scaling dimension of the interaction itself. So at the beginning, when you turn on interaction, it has no effect in terms of gapping, but it is secretly doing the work in reducing its own scaling dimension until its own scaling dimension gets reduced to a point where it becomes marginal and the interaction starts to do the job of gapping. If you further turn on the even larger interaction, it will become relevant and then it will gap out the system. So that is actually the picture. So this figure is what we obtain in DMRG simulation. We can use numerics to calculate the scaling dimension of different operators, and then we can perform our numerics at different coupling strengths of interaction. And at every point, we measure the scaling dimension of this 6 fermion interaction operator, and we can really see that its scaling dimension is indeed secretly dropping, even before the gap is not opening all along before G reaches GC, but still something secretly is happening, that the interaction is getting more and more relevant until the transition happens. So the transition happens when the scaling dimension reaches 2. That is where the interaction becomes marginal, and that leads to a KT transition. That's the nature of the transition. So beyond this point, when G greater than GC, then the interaction gets renormalized in such a way that it becomes relevant and flows strong under RG. So only after G greater than GC that the interaction has an effect to drive all the condensable operator to condense and eventually gap out all the fermions. And when the condensable operator condenses, then the remaining operator in your Lartinger liquid theory that braids non-trivially with the condensable operator will all get gapped. For example, all the fermion operator, one can check that they braid non-trivially. Braid means that this K matrix, K inverse matrix, tells you the braiding of these vertex operators, and then one can check that the fermion all gets gapped because they braid non-trivially with all these operators that condense on the boundary. And that generates a mass gap for the fermion. So that's the idea. And then at the SMG critical point, so we are very interested in this critical point. As I said, we really need to move away from the free fermion fixed point and go to here and try to study what's the effect of interaction, or is there anything we can predict here? So actually, in our numerics, we focus on this region and we try to see what's the scaling dimension of the fermion operator. at the SMG critical point, the fermion operator, intuitively, the fermion operator must have a larger, higher scaling dimension. The reason is that at the free fermion fixed point, the fermion operator has a scaling dimension of 1/2, and it just decay. The fermion two-point correlation decay in a power law manner. But in the SMG phase, the fermion should decay, two-point function should decay exponentially. So that means if you want to smoothly interpret a power law decay and exponential decay, then probably you would imagine that the power needs to get larger and larger until power goes to infinity. Then it's like an exponential decay. So that's the intuition. So we conjecture that the fermion scaling dimension is actually larger at the critical point compared to its free fermion fixed point limit. And that's what we check in our numerics. So because our numerics is performed on a two-dimensional, like we have a two-dimensional quantum Hall insulator which has two edges. So now only on one edge we apply the interaction. So now we can do a control kind of a calculation that on the edge that we apply interaction, we can calculate the fermion scaling dimension there. And on the edge we don't apply interaction, it still remains as a free fermion. So we still can monitor there what's the fermion scaling dimension. And what we can see as a control group on the chiral sector, the fermion still remain gapless and its scaling dimension remain the same throughout, even if the interaction on the other edge is very strong. And the interaction at the critical point, we do see that the fermion has a much larger scaling dimension compared to the free limit. So that's before gapping. And then when you enter the SMG phase, the fermion scaling dimension just diverge. It becomes exponential decay, so you cannot make sense the scaling dimension. So we cannot have any data afterwards. So that's what we see. So this is actually I think one of the features of SMG, that's SMG transition. That's, I think, a general idea is maybe at the SMG transition, fermion will always has a larger scaling dimension. This of course is now confirmed in 1+1D, but I suspect this also applies to higher dimensions. And actually that's one motivation for us to propose field theory such that as fermion fractionalization in higher dimension in order to understand these higher scaling dimension. But I won't talk about that maybe today. There's another alternative way to view this multi-fermion interaction. So this is a 6-fermion interaction, but it turns out it can also be rewrite as a Yukawa boson mediated interaction. So you can write down a Yukawa-Hicks theory where the fermion couples to this Yukawa field phi. Phi is some boson, scalar boson field in a bilinear manner, but this phi itself has some dynamics. So if you start from this Yukawa theory and integrate out this boson field, then one can regenerate this 6-fermion interaction. And it turns out the reason is that it doesn't couple to the boson in the ordinary way. So it's not like a 4-fermion interaction to mediate. Because, for example, these two fermions, psi1 and psi3, you can annihilate them, and that will generate two phi1 bosons. And the two phi1 boson will couple to this psi2 and psi4. So that's the Feynman diagram. So you can see the whole process will involve 6 fermion eventually, but you can still write it as a Yukawa type of interaction, which is mediated by some boson. So as the fermion carry all these 3, 0, 5, 4, 4, 5, and 0, 3 charge, you can also try to infer what's the charge of the boson. For example, the first type of the Yukawa boson carry charge 4, 2, and the second type of Yukawa boson carry charge 2, 4. And then you can show that the whole Feynman diagram charge is conserved. The whole process preserves the U1 cross U1 prime symmetry. But you can have these Yukawa bosons to mediate both interactions. So these are the two Feynman diagrams that correspond to these two 6-fermion interactions. So, but with this kind of understanding, you now can write the full theory as some chiral fermion coupled to some boson, and then there are some boson dynamics. So if suppose these boson field phi1 and phi2 condenses, this will generate bilinear mass for the fermion, because you can, as you can see here, if they have finite vacuum expectation value, then the fermion immediately acquire a mass. But this is also, but if they have vacuum expectation value, phi field will also break U1 cross U1 prime symmetry, because these phi bosons, as we just mentioned previously, they carry non-trivial charge under U1 cross U1 prime. So you can't really condense them. Once you condense them, yes, if you condense them, you provide mass to the fermion, but also at the price of breaking the symmetry. So what can we do? Well, notice that this is a 1 plus 1D system. So in 1 plus 1D, continuous symmetry cannot be spontaneous broken. So if you write down a theory like that, which has a U1 cross U1 symmetry on the action level, then there's no way to break this U1 cross U1 continuous symmetry, even spontaneously at low energy. That's the Mermin-Wagner theorem. So at best, what the boson field can do is not to condense, but to end up in a so-called algebraic long-range order phase, or sometimes called quasi-long-range order phase. Well, the correlation of the boson, instead of in the disorder phase where the correlation decay exponentially, in this algebraic long-range order phase, the correlation of the boson decay in a power law manner. So the boson will have some correlation, which goes like power z. Z is like the space-time coordinate x plus it. And for both flavor of the boson, a equals 1 and 2, it decays in a certain power law manner with a scaling dimension determined by the boson scaling dimension. So what does it mean? This power law decay has two consequences. The first consequence is that the power law decay, meaning that the correlation length of this boson field diverges. There's no length scale. So if the correlation length diverges, that means boson correlation length is much larger than the fermion correlation length, no matter what's the fermion correlation length. A diverging number is always larger than a finite number. So that means the fermion will locally see a gap, because locally fermion will see this boson as if it is condensed. And then it's just at long range, it doesn't have a constant long range order, but every local position, you can imagine that the boson condensed and its correlation length is infinite. So the fermion will just see this local bilinear mass, so that allows fermion to gap opening. And as long as fermion opens a gap, fermion correlation length will become very short. And the fermion correlation length is finite. And in that case, it cannot compete with the boson correlation length. So within the correlation length of the fermion field, fermion will never know that the boson actually is disordered, because fermion cannot see the boson disorder at the long length scale, because the boson correlation length is much larger than the fermion. However, because it is still a power law decay, it doesn't have a constant tail in the end. So it still cannot establish a reliable vacuum expectation value. So then in that sense, there's still no symmetry breaking. So we achieve a case where we do not break the symmetry of the original U1 cross U1, but we still provide fermion some local bilinear mass. And this local bilinear mass is just fluctuating at a larger scale, such that it restores the symmetry. But at the local scale, the fermion still sees the gap everywhere. And then fermion can't tell that the boson actually is disordered, because fermion's correlation length now is much shorter than the bosons. So that's actually a very intuitive picture about what happens in symmetric mass generation. It's essentially the fermion bilinear mass disordered by quantum fluctuation. And then this has important implications for fermion Green's function. And this implication even goes beyond 1 plus 1D. So for free fermion, let's say, so from now on, from this point on, I'm going to jump out of this 1 plus 1D example and talk about something more general in general dimensions. So let's consider some free fermion in D-dimensional space-time, where the action looks like this. Then what's the fermion two-point function? Two-point function is just the two-point fermion correlation. And we know that in the momentum space, if you Fourier transform this two-point function to the momentum space, the answer is this. It's just the inverse kernel of this free fermion. So that's simple. So this Green's function, let me start from the free fermion limit, and I will mention SMG later. So at least in this free fermion limit, when the free fermion has an ordinary fermion bilinear mass, it has a Green's function that looks like this. And the Green's function has several important features. First of all, if you look at the denominator goes to 0 point, actually specify the poles of the fermions, the poles of the Green's function. And the pole actually tells you the on-share condition of the fermion, and then that specifies the dispersion relation of the fermion, which is standard. And based on this dispersion relation, our understanding is that you can define the so-called rest mass. Rest mass is actually the energy gap. It's the kind of E equals mc square kind of mass. So that's called rest mass. Let me call it rest mass. Just bear with me with this definition. It's the energy gap of the fermion excitation. We can also maybe define the inertial mass. The inertial mass is the F equals ma kind of mass, which may not be the same as E equals mc kind of mass, right? So let me call it inertial mass, which is defined as the curvature of the dispersion, inverse of the curvature of the dispersion near the band bottom. So that's also a mass. So for the free fermion case, we can see both rest mass and inertial mass is essentially this m absolute value is related to the absolute value of m. But there is also another mass in the free fermion case. That is the so-called bilinear mass vacuum expectation value. By that, I just mean side-by-side vacuum expectation value. That is also non-vanishing in this case. And that mass has to do with m times some non-universal function of absolute value of m, which is not important. So that mass is also not zero. So you can see in our conventional free fermion, massive free fermion, we have simultaneously 3 mass gets opened. But symmetric mass generation is a mechanism which only open the first 2 mass, but not the last mass. Because you can see the first 2 mass only has to do with the absolute value of the mass. But the last mass has to do really with this mass, whether it's positive or negative. This vacuum expectation value has some kind of, even it can be a complex number. It can have a phase factor there. So only the last mass has to do with m itself. The other mass has to do with the amplitude of the m. So symmetric mass generation essentially is you keep the amplitude of the mass, but you disorder the direction of the mass such that you don't see any fermion bilinear expectation value and you will not break the symmetry. Because this fermion bilinear mass term, once it has a vacuum expectation value, usually breaks symmetries because it transforms non-trivially under the symmetry. So that's essentially the idea. So based on this idea, if we can just interpret as disordering fermion bilinear mass without turning off its amplitude, then we can do something non-trivial to this Green's function, to this fermion 2-point function. We start from the free fermion, free massive fermion Green's function, and we just look at this Green's function. We say, oh, so this mass on the numerator, it fluctuates with the symmetry transformation. I need to turn it off. But on the denominator, it enters as the absolute value square, so it doesn't matter. The amplitude doesn't still have a non-trivial average, but the mass itself has a trivial average. So that means probably I want to rewrite the Green's function in this form. So then there's a conjecture that this is the Green's function of the fermion 2-point function in the SMG phase. So the difference between a free massive fermion and an SMG fermion relies in its 2-point function. The 2-point function has an important difference on the numerator, such that one has the mass term that breaks the symmetry. And the other, you can see under symmetry transformation, mass term just rotates. But this Green's function now is fully symmetric under the rotation of the mass term. So that is what we mean by symmetric mass. It provides a mass term to the fermion on the denominator as a pole. If you look at the pole of the Green's function, you can still see that the pole or the dispersion relation of the fermion is completely the same as usual. But it doesn't lead to symmetry breaking because you eliminate the symmetry breaking mass on the numerator. And then that gives you this non-trivial Green's function. But this Green's function, since it's different from the free fermion case, it must have some other additional structure where you can prove the difference, right? And then our proposal is that the difference lies in what? Lies in these zeros. Because this Green's function, you can see once you don't have the mass on the numerator, then the Green's function actually has additional zeros, which are these 2 lines where the horizontal axis is momentum, the vertical axis is a frequency. When the momentum equals frequency on this light cone, basically, you can see the K mu actually kind of is zero in some sense. So along this light cone, you will have a vanishing numerator, and then the denominator, but the denominator is not vanishing. When K equals 0, the denominator is still controlled by mass, but the numerator will vanish. So you will obtain lines of, or a cone of zeros in your momentum energy space. So that cone of zeros, or that Green's function zeros, is the smoking gun feature of symmetric mass generation. So we propose that every symmetric mass generation phase, if you inspect its fermion 2-point function or the Green's function, you should see that in the momentum energy space, that there are always be regions separated by fermion Green's function zeros, and this zero must also touch the zero energy and zero momentum point. So the Green's function zero is specified by the region between the determinant of the Green's function less than 0 and determinant of Green's function greater than 0. Because in general, Green's function is not a number, it can be a matrix. So what do I mean by it is 0? I really mean that its determinant is 0. So this Green's function actually is also proposed by Simon, and also among the same time, we'll also write down the same form in this paper. So essentially, that's what I said. In terms of pole, you still have the same quasi-particle excitation. It's still well defined. The quasi-fermion quasi-particle is still well defined above the gap with the finite rest mass and the finite inertial mass. So symmetric mass generation really brings rest mass and inertial mass to the fermion, but it doesn't bring fermion bilinear mass term. There's no bilinear condensation. The reason is that the side-by-side expectation value is nothing but the momentum frequency integration of the Green's function, because Green's function is side-by-side, essentially. You just need to integrate over the momentum space. And then this integration must vanish. The reason is because the Green's function now is odd under K. You can see this is an odd function of K mu. So integration is going to vanish by symmetry requirement. And then the fact that this Green's function is odd under K is also required by the Green's function 0, that you must have a 0 of your determinant of the Green's function at the 0 frequency. And then there's actually a non-perturbative argument for why the determinant of the Green's function must be 0 at 0 frequency. The reason is that you can view, for example, let's go back to this 1 plus 1D case. And let's view this 1 plus 1D system as the boundary of a 2 plus 1D domain wall between fermion SPT phase and the trivial phase. So we can treat this 1D gapless fermion system as certain boundary between fermion topological phase and trivial phase in 2 plus 1D. So along this boundary, the 1D fermion is maybe a gapless. So you can start from such a scenario, and then you can, along the boundary, you can turn on interaction. So before I turn on the interaction, the full boundary is just gapless 1D fermion. And for gapless 1D fermion, you can see the determinant of G inverse is 0 because they are pole at 0 energy. So the pole means that the Green's function is going to diverge at 0 energy. So that's what happens for gapless. But then you turn on interaction gradually in the space in the spatial direction along this direction until you reach a point where interaction is strong enough and drive the system into SMG. But why do I still need some fictitious boundary here? It is because if you calculate the topological index in the trivial phase, it is going to be different from this certain topological index in the interacting in the SPT phase on the other side. So the index that I propose is that people actually, it's not I propose, it's people propose you can start from the fermion 2-point function and evaluate certain G inverse partial G kind of thing. And then you do a momentum space integration. That is basically TKNN integer or something like that. That's basically, you can do that on the free fermion level and calculate the index on both sides. And this calculation is valid because I didn't turn on any interaction on both sides. I only turn on interaction along this boundary. So I can still well define this index here. But this index is an integer, and then this integer cannot jump abruptly, cannot jump smoothly. It must jump only because this integration encounters certain singularity. And this integration is singular only if the integrand inside this integration diverge. So the index can only change if there's some divergence in the integrand, and then the integration is not well defined. Then passing that point, you may have a different index. So the integrand can only diverge either G inverse has a divergence or G has a divergence. You can see G and G inverse has the same, it's almost on equal footing in this expression. So for free fermion case, when the boundary is gapless, when there's no sufficient interaction to gap out the fermion, then basically the index jump because the determinant of G inverse goes to 0, meaning that G diverges. The Green's function diverge at the 0 frequency because it touches the pole of the gapless fermion. But if the fermion gets gapped by some interaction, then you no longer have any pole at the 0 energy. So your determinant of G inverse is no longer 0. So G, meaning that G does not diverge. Then if G does not diverge, G inverse must diverge. G inverse diverge means that the determinant of G equals 0. Then G inverse diverge, essentially. So you must have these non-trivial determinant in order, or you must have this 0 determinant either in the G inverse section or in the G section in order to drive this divergence of the integrand and in order to explain the abrupt change between this index on both sides. So this is a topological requirement that we must have Green's function 0 in the SMG phase. And that statement is actually consistent with just what we said, this form of the Green's function. So
may I ask one question?
Yeah.
So can you explain, so is there any relation between the Green function 0 and the variation of the vacuum expectation value?
Yeah. So it's not directly related. I should say it all comes from the fact that the Green's function is an odd function of momentum. So that statement simultaneously applied to here. If it is an odd function, then the space-time integral vanish. If it is an odd function, then at omega 0, you must have a point. Actually, at omega nk equals 0 as an odd function, right? It explicitly tell you that there is a point. There is a point where the determinant of G vanishes.
So you cannot directly using the Green function 0 to show that the vacuum expectation value must be 0. You need to rely
you can directly using this fact that the Green's function is an odd function in the SMG phase to show that the vacuum expectation value must vanish. Actually, if you put the plus m here, immediately it is not an odd function in K, and immediately you get the non-trivial vacuum expectation value here. So it's all consistent with the fact that what we do is we remove this m on the numerator and then immediately restore the symmetry, and that also leads to the oddness of the Green's function. And this oddness is just another way of formulate that is just saying that the Green's function must have 0 at 0 frequency. So this is a consistent story.
So by the way, do you have comments about the zeros and the poles of the Green function with respect to the generalized Latinger theorem?
I think that's a very good question. That's like because in Latinger theorem, generalized version, that Latinger volume is defined by both pole and 0. So you may wonder whether, for example, today I talk about symmetric mass generation only for Dirac fermion, where you don't have a Latinger volume. But you can also ask for fermion which has a Fermi surface, Fermi liquid, that you have a Latinger volume. Can I also apply interaction to gap out the Fermi surface trivially? And if that happens, there must be some consequence left over because you can't violate this generalized Latinger theorem. You can't just get rid of all these fermion without leaving any consequence. So the idea is that it leaves zeros on the original Fermi surface. You replace the Fermi surface by original is a pole by 0, replace pole by 0. So you still don't violate Latinger volume, but you can gap out fermions on the Fermi surface as well using the same idea by interaction. So that's something we are starting right now, actually. We haven't finished that project, but I think in general, that's what everything what I want to say. So the summary slides, let me go through that. So the symmetric mass generation in general is a novel mechanism to give fermion a mass without bilinear condensation, this allowing gap out the fermion without breaking the symmetry. So that's the take-home message. And we discussed that there are two conditions. One is that is more well accept that you need to cancel all the anomaly, but that's just one condition. And you also need to check that your interaction really satisfies the gapping condition. This part is less well understood. I think it's a future direction, especially this condition.
Sorry, Yizhuang.
Yeah.
Sorry, just before you move on, can I ask a question regarding the Fermi surface comment that you made?
Oh, okay.
Because you said that at least in this chiral fermion model, chiral fermion model you've written down, you said that you can't put in mass terms, right? So how do you get a doping term and get a Fermi surface? The mass terms are gonna break the U1 prime symmetry.
Mass term and doping term are still different term. Mass term is side by side, doping term is side dagger side.
But isn't that also forbidden?
So another thing is that we are changing the symmetry. When we go to it's completely different system. I'm not saying we start from this system and turn on doping. No, I'm not doing that. I'm starting some other system where fermion already has doping. So then the symmetry, any symmetry that doesn't allow you to dope the system is not a symmetry in my system.
Yes. So I was thinking about that.
I'm not doing that thing. I just want to start from some Fermi liquid. Well, maybe Fermi liquid nowadays we know that Fermi liquid has the U1 loop group symmetry as an emergent symmetry energy. So what I want to preserve is this U1 loop group symmetry. And then I want to discuss, if you want to preserve this loop group symmetry, it's also very strong symmetry. And then if forbidden all the fermion bilinear mass term, you can't really gap out the Fermi surface by superconductivity that's going to break this U1. You can't break it by gap out by charge density wave that's going to break cancellation, which is also part of the loop group of U1. So what can you do? Can you use interaction to achieve something non-trivial that can still doesn't violate anomaly constraint? Of course, if you only have a single Fermi surface, you may have anomaly, because this loop group U1 has a Fermi surface anomaly. So you first need to design some nice way that you cancel the anomaly, and then you think about ways to use interaction to gap out the fermion. So that's the idea over there. So that's completely orthogonal to this model itself.
Yeah, thank you.
Yeah. Okay, so that's essentially what I want to say. And then I want to say that in terms of the features, this I didn't mention that in higher dimension, it turns out we can use some fermion fractionalization idea to understand SMG transition. So the SMG transition turns out to be some deconfined quantum criticality, so that relates to some non-trivial CFT with enlarged fermion scaling dimension. And then inside the SMG phase, there's also an important feature, that's what I just mentioned, that you have fermion Green's function 0. And then it has many applications, such as lattice regularization, for standard model of grand unified theory. Recently, people also apply it to search for new candidates of non-SUSY duality. And Juven also has a paper recently on a new perspective on strong CP problem, maybe solvable by ideas of symmetric mass generation. And then it also allows us to construct interacting SPT phases. Is also related to SPT phase in condensed matter physics, and potentially provides new insights. That's my last comment to pseudo gap physics in high temperature superconductor, where the goal is to gap out Fermi surface without breaking symmetry. So the idea to remove fermion from low energy without breaking symmetry by interaction, I think, is a very general thing. And then if we understand symmetric mass generation better, it can have many more applications. So that's it for today. Thank you for your attention.
Thank you very much. May I start with a very trivial question? So you mentioned there are different type of mass terms, and you have a raster mass. I think this corresponds to the charge gap in the condensed matter language. In the condensed matter, we also know there are spin gap and a neutron gap. We understand them. Are they correspond to different symmetry charge of the fermion operators?
Yeah, maybe. So if you have a charge gap without the spin gap, that probably means your fermion is already spin charge separated. So then probably you want to discuss this mass for charge on and spin on separately. So you can't really just use a simple idea of fermion mass to simultaneously describe a situation where you have a charge gap without a spin gap.
So the neutron gap just means that the fermion doesn't carry charge.
Yeah, maybe. I may not be so familiar with every this notion, but what I know is that right, in quantum spin liquids you can have charge gap, but you don't need to have a spin gap. Spin excitation can be gapless, but in that case, fermion original electron need to fractionalize into bosonic and spin-ons, things like that. So.
And the symmetric mass generation, is anything connected to the multi-insulator, interaction-driven multi-insulator? Are they same or different?
I think they are the same in the sense that they correspond to the multi-insulating phase when the filling is integer. So when the filling is integer, we say it's a band insulator, meaning that's a trivial insulator. But multi-insulator can still exist. Integer filling is a strong interaction version of. So here, for example, all our system has 0 Latinger volume. So essentially, it's in terms of filling, it's like an integer filling. And then in that case, if you can have some multi-insulator, that's called the symmetric mass generation. That's essentially the idea, driven by interaction. Yeah.
So it's a band insulator plus interaction?
Yeah.
Okay.
Band insulator, if it is already insulating, usually you don't need interaction, right? But there are band insulator, which in terms of feeling is like a band insulator, but in terms of band structure, it's still not, like wild semi-metal. And then in that case, you can try to ask whether I can use interaction to drive things. Because the reason that I require integer feeling, I want to cancel anomaly. If the filling is not integer, then there's a LSM theorem that's basically saying that the system is anomalous. You cannot enter a multi-insulating phase without any consequence. You must develop topological order or something else. So that's why I don't want to say it's multi-insulator in the conventional sense, because conventionally multi-insulator comes with LSM anomaly, and that leads to non-trivial consequence. But here it's really the multi-insulator without anomaly. So that's like a band insulator plus interaction. But in terms of dynamics, it's same. It's still because of interaction, it gives a gap to the fermion. So in that sense, it's the same. Yeah.
I see. So the like interaction driven, if you have strong interaction in surface topological insulator, and like time reversal invariant fermion, this is not included.
Yeah. Those topological order is not included because that requires anomaly, and SFG is specific to anomaly-free systems.
Yeah. So Simon, you can unmute.
Yeah.
Yeah, I am. Sorry. Yeah, I just wanted to make a point. Thanks for a very nice talk. Actually, that was great. That you can build mirror models, of course, using these Kähler-Dirac fermions as well. And one advantage of those things is the anomaly structure of those theories survives under discretization. So you can connect directly from your lattice model into the continuum in a way which is kind of it's very clear when symmetric mass generation will work or not. So that's one part of that. And the second part of that is it looks like you can embed certain types of chiral theories into those Kähler-Dirac theories in such a way that I think you have another potential route to construct chiral lattice gauge theories using this sort of by embedding chiral fields into these Kähler-Dirac fields. So there's just I mean, I'm sure you're probably aware, but I just wanted to make the point that there are other routes to using symmetric mass generation involving lattice fermions of different types. That's all.
I see.
Yeah, I mean, maybe you haven't seen my most recent paper, but it's
I should maybe read those.
But it's kind of amazing that these things have exact anomalies even for finite numbers of degrees of freedom, and you can follow those anomalies into the continuum and they give you direct constraints.
I see. I really wish to talk with
phases.
you more on that maybe later. Yeah.
Yeah. Well, I guess we're going to chat again at some point soon.
Yeah.
So yeah. Anyway, just a quick comment. Thanks. Thanks for the talk.
Yeah.
Any other questions? So if not, let's thank you, Yizhuang, again. Thank you for this very clear talk. We enjoyed a lot. Thank you.
Thanks everyone for coming.
Yeah.
See you.
Thank you.
See you.